Video is going to teach you guys how to react metals and nonmetals together. But first, before we get there, we have to learn what a half reaction is. You're going to use this to predict the charge of an ion. It involves Lewis structures, so you have to use your periodic table to come up with the Lewis structure for each of these elements. But then also there's different versions of this. There's a math version that's preferred, but there's also more of a visual idea that you could use. I would prefer if you use different colors, like maybe a pen to go with your pencil if you're going to do the visual version, because otherwise it's kind of hard for me to follow along with your work. And it's hard to differentiate later with a different thing that we're going to do. So, whatever it is you prefer, that's fine. Just make sure you always show your work for this kind of stuff, because for right now, right, you're just learning how to do this. You have to show your work. Later, this should be kind of second nature, so you don't have to show your work as much. But at least on the worksheet that you're going to do after this, make sure you're showing your work. Okay, so a half reaction is pretty simple actually. All I need to know is, okay, magnesium is in group 2 on my periodic table. It's in the second column. So it has 2 valence electrons, and magnesium being a metal would be much more likely to lose electrons than gain electrons, right? So a half reaction looks like this. I have those 2 electrons to lose, right? I'm always going to lose or gain trying to get a full shell. For magnesium, it's easiest to lose 2 electrons to revert to an inner shell. So it can look like another element, right, that would have a full shell, right? Magnesium is near neon on the periodic table. If it lost 2 electrons, it would look just like neon. It would have the same electron configuration as neon, and neon's super stable. So it wants to lose 2 electrons to look like neon, but for our purposes, we say minus 2 electrons and have a reaction arrow, and you end up with a magnesium atom over here that doesn't have any dots around it. That's how I know that it lost those 2 electrons, but it also has a charge, right? Magnesium, after it loses 2 electrons, is going to have a +2 charge because it still has the same number of protons as it did originally. It just has 2 less negatives than it had originally. So it's going to have a +2 charge. This is the half reaction that I've shown here, and this is one way of showing your work. Again, the dots represent electrons. So losing 2 electrons, my magnesium is now empty and has a +2 charge. Right? Nonmetals, on the other hand, you do a little bit differently. Right? Nonmetals, instead of losing electrons, they tend to gain electrons. My phosphorus over here is in group 5. So in order for it to be happy, it wants to gain 3 electrons, because that's how it's going to end up looking like argon, right? And being stable like argon is. So if I can get that octet rule, excuse me, writing the wrong letter for a second. Phosphorus wants to gain 3 electrons, but when it does, it has the same electron configuration as a noble gas. I need to put dots all the way around that phosphorus because now it's full, right? But with those 3 extra electrons, it also has a charge, has a -3 charge. So again, this is another half reaction, right? So you either subtract electrons or add electrons. You either end up empty like the magnesium did or full like this phosphorus, but either way I'm representing electrons being gained or lost, and that's what I need to do for these reactions between metals and nonmetals, right? Potassium here is in group 1. It's a metal. It would be much easier to lose 1 than to gain 7, so it should be pretty obvious what's going to happen here. If you choose to do a different style of work for this, other than those half reactions with the math style up above, right, with a different color, I would be okay with you thinking about, okay, I'm going to lose that 1 electron. Again, that would give you a charge, and it'd be a +1 charge. Sorry, I missed the cross there. Because losing 1 electron, you still have the same number of protons as you did before, so you got more protons than electrons. Potassium ends up with a +1 charge, and it currently, without any electrons, would look like argon, right? So it'd have a stable configuration. Whereas this sulfur over here, should have 6 valence electrons, so 2 pairs, 2 singles. In order to be happy, again, if you had a different color, you could just bring in electrons, and now it's full. But now it has 2 more electrons than it normally does, so it also has a charge. It has a -2 charge, right? That's another option if you wanted to show your work, right, more visually. That'd be fine. But you can't use this, you can't use a pencil for everything, because I can't tell the difference between the dots that are new and the dots that are old, right? So if you're going to show work like one of these two, I need you to use a different color, right? Maybe a pen to go with that pencil, maybe a colored pencil. I don't really care what you do, but you'd have to find some way to differentiate. Otherwise, like I said, you can always do the math version. Tin is kind of ambiguous at first, right? This is one of those ones you actually do have to think about. Is it a metal or a non-metal? Because if it's a metal, it's going to lose. If it's a non-metal, it's going to gain. Because tin is a metal, it should lose those 4 electrons so that it can end up being empty. It should end up with a +4 charge, which is basically just the opposite of what you did over here. This is a minus, you end up with a plus, right? Always works out that way because you're losing negative charges. That's why it ends up positive, right? Whereas the bromine over here should have 7 valence electrons because it's in group 7. In order to be happy, it would want 1 more electron, and that's what's going to make it negatively charged. But again, make sure that you have all dots accounted for, all electrons accounted for, right? And I can tell the difference between before and after here because it had 7, now it has 8. That's why it has a -1 charge. But I didn't get a before and after on this sulfide picture up here. That's why you have to use a different color. I can see what's happening if you have a different color, but otherwise I can't. So you got to show your work.